Hey everyone, in the next few videos we will look at some regularity conditions that are often imposed on functions in order to obtain better oracle complexity of various algorithms. These are not necessarily satisfied by all functions, but in practice we often try to work with functions that actually do satisfy these or sometimes change the formulation so as to satisfy the regularity conditions. We begin with the notion of Lipschitz continuity of a function. A function f is said to be Lipschitz continuous if it satisfies f of x minus f of y absolute value less than equal to LF times norm of x minus y. If a function f is differentiable, then the Lipschitz continuity implies that norm of gradient of f of x is less than equal to LF. Conversely, if the gradient is bounded, then the function is Lipschitz continuous. If f is not differentiable, we simply replace the gradient with the subgradient, that is the norm of gx is bounded by LF, where gx is a subgradient of f at x. So this is the notation for the set of all subgradients of f at x, which is called the subdifferential set. Let us look at some examples. The function sin x is clearly Lipschitz continuous. You can verify by differentiating and bounding the gradient. But the functions e raised to the power x and x square are not. Next, let us consider the Lipschitz continuity of functions that are convex and are defined on a compact set. This is useful in the context of algorithms that operate in a compact domain. A set calligraphic x is said to be compact if it satisfies max over x comma y in calligraphic x, norm of x minus y less than equal to b less than infinity. In other words, we are saying that the maximum distance between 2 points on this set is bounded. There is a close connection between Lipschitz continuity and convexity for such compact spaces. Suppose that f is a proper closed convex function on a closed compact space calligraphic x that lies in the relative interior of the domain of f. Then f is Lipschitz continuous. This is an interesting result as it allows us to infer Lipschitz continuity of a function based on its convexity. Let us take a look at some examples. Consider the function 1 over x defined over open interval 0, 1 closed interval. While the function is proper closed, we are working with an open set. Hence, 1 over x is not Lipschitz continuous over this open set. However, if we meet our requirements by setting calligraphic x equal to c, 1 for c greater than 0, then the function becomes Lipschitz continuous. Next, consider x square defined over R. Here, we do not meet the criteria of compactness of the space because R is not compact and therefore the function is not necessarily Lipschitz continuous. However, x square is Lipschitz continuous on any interval a, b, where a and b are any real numbers. Finally, consider minus square root of x with domain 0 to infinity. Then minus square root of x is not Lipschitz continuous over the set calligraphic x equal to closed interval 0 to 1 because the closed interval 0 to 1 is not a subset of the relative interior of the domain of the function, which is from 0 to infinity. But it is Lipschitz continuous over the closed interval 1, 2, which is actually a subset of the relative interior of domain of f. Next, let us consider the notion of smoothness. A function is said to be L smooth over calligraphic x, subset of relative interior domain of f, if it is differentiable over calligraphic x and its gradient satisfies dual norm of gradient f of x minus gradient of f of y less than equal to L times norm of x minus y, where we have the norm on the right hand side and the corresponding dual norm on the left hand side. The requirement that x is in the interior of the domain is necessary because differentiability of the function on the boundary of the domain will not generally hold. In other words, the gradient of the smooth function is Lipschitz continuous. As in the case of Lipschitz continuity, an implication is that if the function is twice differentiable, then its second derivative norm would be bounded by L. You can similarly define higher order smoothness conditions like the smoothness of second order or third order derivatives and so on. The Lipschitz continuity of the Hessian is, for instance, used in studying the Newton method. In order to study first order algorithms, however, this definition of smoothness is sufficient. Let us take a look at a simple example to begin with. Consider a quadratic function f of x equal to half x transpose qx plus r transpose x, and observe that its gradient is given by qx plus r. So gradient f of x minus gradient f of y is equal to q times x minus y, and therefore we need to bound its norm with some multiple of norm of x minus y. For this purpose, we recall the definition of the operator norm, which is given by PQ operator norm of Q equal to max over all x not equal to 0 LQ norm of QX divided by LP norm of x. So from the definition of the max operator, we therefore have that operator norm of Q is greater than or equal to LQ norm of QX divided by LP norm of x for all x not equal to 0. Or equivalently, LQ norm of Qx less than or equal to operator norm of Q times LP norm of x. Applying this result to x minus y, we have that LQ norm of Q times x minus y less than or equal to operator norm of Q times LP norm of x minus y, which holds for all P and Q greater than or equal to 1. But we are only allowed to use dual norms in the definition of smoothness here. So we have to choose P and Q such that LP and LQ are duals of each other. This is the case when 1 by P plus 1 by Q is equal to 1. In that case, LP and LQ norms become duals of each other, and we get the required form for smoothness. Therefore, the quadratic function f of x is norm of Q, P, Q, smooth with respect to the LP norm, such that 1 by P plus 1 by Q is equal to 1. In the special case when P is equal to Q equal to 2, the 2, 2 norm of Q is lambda max of Q, which is the largest eigenvalue of Q. So in the Euclidean space endowed with L2 norm, the quadratic function is lambda max Q smooth. Let us look at some important properties of smooth functions. Perhaps the most important property is the so-called quadratic upper bound property, which is as follows. Consider an extended real valued function f that is L smooth over some calligraphic x in the relative interior of the domain of f. Then it satisfies f of y less than or equal to f of x plus gradient of f of x inner product with y minus x plus L by 2 norm of x minus y square for all xy in calligraphic x. To establish the proof of the quadratic upper bound, we have to use the fundamental theorem of calculus, which says that f of y minus f of x equal to integral from 0 to 1 inner product of grad f of x plus t times y minus x with y minus x dt. You might have seen the fundamental theorem of calculus earlier. It is nothing but the relationship between the process of differentiation and integration. We are basically saying that the integral of the gradient between 2 points is equal to the function value difference between those 2 points. In the first term of the inner product, let us add and subtract gradient f of x so as to write the equality gradient f of x inner product with y minus x plus integral 0 to 1 grad f of x plus t times y minus x minus grad f of x inner product with y minus x dt. Then let us take the first term to the left and take absolute value on both sides so as to obtain absolute value of f of y minus f of x minus gradient f of x inner product with y minus x equal to absolute value of integral from 0 to 1 gradient f of x plus t times y minus x minus gradient f of x inner product with y minus x dt. At this point, we want to take the absolute value inside the integral, which is basically the use of the triangle inequality, yielding the bound f of y minus f of x minus gradient f of x y minus x absolute value less than or equal to integral from 0 to 1 absolute value of inner product of gradient f of x plus t times y minus x minus gradient f of x with y minus x dt. Now let us use the generalized Cauchy-Schwarz inequality, which you have already seen, which says that inner product is less than or equal to dual norm times norm. Using it here, we get integral from 0 to 1 dual norm of gradient f of x plus t times y minus x minus gradient f of x times norm of y minus x. So now we have it in the form that we can directly use the Lipschitz gradient assumption and bound the norm of gradient f of x plus t y minus x minus gradient f of x with norm of t times x minus y. Taking the scalar t out because it is from 0 to 1, the right hand side becomes integral from 0 to 1 t times L times norm of x minus y square dt. Integrating with respect to t, we get L by 2 norm of x minus y square. So this gives us the required quadratic upper bound. So we have seen so far that smoothness implies quadratic upper bound. However, the converse is not true. That is, the quadratic upper bound does not imply smoothness. In other words, the function could have an upper bound but still not be smooth. For example, any concave function can be upper bounded by a tangent line by definition, but need not be smooth. As a specific example, the function minus absolute value of x is a concave function that can be upper bounded by a line, but is not differentiable at x equal to 0. Note that since f is smooth, so is minus f. So we have a similar lower bound which is stated as f of y is greater than equal to f of x plus gradient f of x inner product with y minus x minus L by 2 norm x minus y square. For a given x, we have seen two kinds of bounds. The right hand sides of both the bounds are quadratic functions of y. The right hand side of the upper bound is a convex quadratic function, while the right hand side of the lower bound is a concave one. These inequalities provide a bound on how quickly the function value of a smooth function can change in either directions. Let us take a simple example, f of x equal to 1 over 1 minus e raised to power minus x. It is clearly differentiable. Generally, finding L might be a bit tricky. However, in this case, since it is a scalar function, I know that its smoothness parameter L is also the maximum value of its second derivative. So I can plot its second derivative with respect to x and see that it takes a maximum value that is slightly less than 0.1. So we can take L is equal to 0.1. Let us plot the upper and lower bounds of this function at x equal to 1. The upper and lower bounds are denoted by dotted lines and have the same slope as f of x at x equal to 1. The upper and lower bound at different points will also have the exact same shape, but will be translated to that point. So we have derived a property of smooth functions. The remaining properties we will only be writing down without proof, and you need to derive them yourself. They are all important and will be very useful later on. So all of these properties hold for extended real valued function f, that is L smooth over a convex set calligraphic x, in the relative interior of its domain. We begin with a specific property that is only valid for inner product spaces, that is spaces where the norm square is equal to inner product of x with itself. Then the function g of x equal to L by 2 norm square of x minus f of x is convex over calligraphic x. The result is interesting as it relates smoothness of function f to the convexity of this function norm x square minus f of x. But it is only applicable to inner product spaces and not valid for something like L1 norm space. The proof of this result is not too complicated and just requires us to verify the first order condition for gx. And note that the gradient of gx is Lx minus gradient of f of x. Next we have the following property, which is gradient of f of x minus gradient of f of y inner product with x minus y is less than equal to L times norm of x minus y square, which is an immediate implication of the smoothness property. Then we have the zeroth order characterization of smoothness, which is that f of theta x plus 1 minus theta y is greater than equal to theta times f of x plus 1 minus theta times f of y minus L times theta times 1 minus theta divided by 2 norm of x minus y square. We have observed that we did not use the gradients to specify this property, so it's a zeroth order condition. You can prove this by writing the quadratic upper bound at z is equal to theta x plus 1 minus theta y for points x and y, and then adding the two inequalities so that the gradient dependent terms cancel. Finally, a second order characterization of smoothness is also possible for functions that are operating in Rn and that are twice differentiable. Such functions are L smooth if and only if the PQ operator norm of the Hessian at any x is less than equal to L, where P and Q are greater than equal to 1 and 1 by P plus 1 by Q is equal to 1. We have already seen an example of this property in the context of quadratic functions, where f of x is equal to half x transpose qx plus r transpose x, for which case you can see that the Hessian is a constant matrix Q and therefore its smoothness coefficient L is equal to the PQ operator norm of Q. So that's it for this video, where we saw a lot of properties related to smooth functions. We will be using these properties throughout the course. We will continue in the next video with the discussion of another regularity condition, that is the strong convexity.